I'm going to take a few minutes and just go over the outline I gave you. Keep in mind this was the practice for last year, so there are going to be a few differences as we go along. Also on the definitions, this is just some of the terms. You should know all of the key terms that we talked about in the chapter. So the mass number, sum of protons and neutrons, isotope would be you have the same number of protons and a different number of neutrons. Synthesis reaction is when you combine two things together and you get a compound. Metalloids are some of the elements that are on the dividing line between metals and nonmetals. And if you look on the sheet that I gave you, I think the color that they're colored pink or red. And then Dalton's atomic theory we talked about in class, so just make sure that you know the different parts of Dalton's atomic theory. Also, you should know which parts of the theory are not, in fact, true or thought to be true today. I went over this in one of the videos that you were assigned, but let me just briefly say that if you're given this sort of sketch of either this or the Rutherford experiment, the Goldwell experiment, you should be able to label the different parts, which are actually labeled here, and also you should be able to say what happened in the experiment. So in this case, when a high voltage difference was applied, what was discovered was that, so here, let me see if I can, here they noticed that there was a beam of particles. And the interesting thing was that these particles that were moving along this cathode ray tube could be bent, and they were bent toward a positive charge and away from a negative charge. Also, they got the same type of particles, whether they used, or no matter what particular metal that they used. So this was really the first subatomic particle that was discovered, and this is basically considered the discovery of the electron. So I will give you a chart, maybe not with quite as many examples. Make sure that you can fill in the missing information, and that just really is a matter of knowing the definition of what mass number is, the fact that the number of electrons is equal to the number of protons in a neutral atom, and if you have a negative charge, like you do here, for example, then that means that the number of electrons goes up by that amount of the negative charge, and if you have a positive charge, like you have in this example, that means that you have fewer electrons. So although we made some mole calculations the last couple of weeks, on this particular test you really just need to know the kind of theoretical basis for how we come up with the idea of a mole and also the idea of Avogadro's number. So this is a chart that's a little similar to the one that I went over in class. The key points here are that although, here let me do this, so although the masses of two different atoms, in this case oxygen and sulfur, are different, if you take that mass, so in this case 16 AMU and 32 AMU, the ratio of the atoms is going to be, here is going to be 1 to 1, but the ratio of the masses will be 1 to 2. And as long as you continue, so that would be over here, as long as you continue to take the same number, whether it's 1, 10, a dozen, a million, or a mole worth of atoms, then the ratios are going to stay the same. So, and then the other thing that you need to know is just the definition of a mole is 6.02 times 10 to the 23rd of anything, but in this case atoms. So down here, this is basically a summary of what I was just saying. And for the last question that says, explain why it's not necessary to know how many atoms are in one mole to finish the last row of the table, it's because as long as you keep taking the same number, and you add them up, then you're going to end up with the same ratio. In other words, as long as every time, whatever you take of oxygen, you take that same number of sulfur, then the weight ratios are going to be the same and the number ratios will be the same. So on this test, you will not have these kinds of questions unless you have them perhaps as a bonus, but this is something you probably could do right now, but we'll wait and do it for Chapter 3. We're going to talk about the periodic table in a lot more detail later on, but for now, you should know that here, that this is the alkali metals, and in this column, these are the alkaline earth metals. This section through here are the transition metals. This column is the halogens, and in the last column, these are the inert gases, or sometimes they're called the noble gases. The other thing is you should know that this line here, this little zigzag or staircase line, separates the metals from the nonmetals. And I mentioned to you earlier that on your other sheet that I gave you, you have the particular ones along here that are metalloids. So far we have 3 different ways that we can represent molecules, and keep in mind this is only for molecules. So one thing that we can do is we can represent the where all the atoms are attached. So this shows, each atom and how it's attached to every other atom. So this is called the structural formula. If we take this formula and condense it down, so that, for example, this last group, the C double bond oxygen and the single bond oxygen and hydrogen are all condensed down to this group, then that's referred to as the condensed structural. The other type of representation that we have is just where we list the type of and number of each atom. So we have 2 carbons, 4 hydrogens, and 2 oxygens. The last thing that you should know here is that these parts in this area, the kind of reddish parts, are referred to as the functional group. And a functional group is a group of atoms that determines the reactivity of a particular molecule. So this particular one would be called, this is a carboxylic acid. This is a halogen group. So you're responsible for the lab where we combined hydrogen and oxygen, and we found the best ratio, which we refer to as the stoichiometric ratio, and the lab on double replacement reactions, the precipitation reactions. So you need to be able to use the solubility rules. You don't have to memorize them, but you need to be able to use them so that you can write the net ionic equation. Here are the answers, not so neatly, but anyway, here are the answers to one set of compounds where I give you the formula and you have to write the name. And then the next set where I will give you the name and you have to write the formula. So I've given you all the rules for those. Just be sure that you go over those and that you're able to do that. This would not be a question on a test, but it could be a bonus. So it kind of takes advantage of 2 different ideas. The conversion practice that we did in Chapter 1, plus the idea of Avogadro's number that we talked about in Chapter 2. So if you can't do this, it's not really a problem, but if you want to take a look at it as an example, just an example, it doesn't mean that you will have this exact problem or necessarily one similar to it, then that would be great.